Hello, we're back again with another lesson for our subject Engineering Calculus 2. I'm still your lecturer for this subject, and our lesson for today would be integration techniques. So we've learned some fundamental theorems from our earlier topics, and generally the U substitution technique, and now we will be learning some more integration techniques. So these are our intended learning outcomes. So at the end of this lecture, you should be able to evaluate an indefinite integral using the following techniques. The first is integration by parts. Second is trigonometric substitution. The third is integration by partial fractions. So for this lecture, we will be learning to evaluate an indefinite integral using integration by parts. So first, let's try to derive the formula for integration by parts. So we'll start with we have a formula for getting the derivative of the product of two functions. So we have two functions, f of x and g of x, so that would be f of x times g of x. And to get the derivative of that, if you can recall from your calculus 1, you just need to multiply f of x with the derivative of g of x plus g of x multiplied by the derivative of f of x. So to easier visualization, or to apply some mnemonics to it, let's take f of x as u and g of x as v. So this one would be the same as this one. So taking the derivative of u times v, that would just be equal to u times dv, derivative of v, same thing, plus v times derivative of u, or uv equals u dv plus v du. So this is basically the product rule for differentiation. So if you can recall, what we are doing here in calculus 2 is to take the antiderivative. So the previous techniques that we've learned, like the U substitution, is basically inversing the chain rule for differentiation. So for this one, this is the product rule for differentiation. We will take the antiderivative of it as well. Okay, so we will take the integral of the derivative of uv, and that would be equal to the integral of u dv. So if you can recall how to integrate a function separated by plus and minus, you will just distribute the integral sign. So we integrate u dv plus the integral v du. So let's actually operate on this. So okay, let me rearrange it here. So the derivative of the integral of a derivative will just cancel out, right? So you have u times v, and that would be equal to the integral u dv plus v du. So if we rearrange it and take u dv alone on the left side, and let's take VDU on the other side, we will have this formula: the integral of u dv equals uv minus the integral v du. Okay, so what do we have here now? So on the left side, you notice that we have a function that needs to be integrated. Essentially, it's u dv, and that is just equal to u times v, or the integral of dv, minus the integral v times the derivative of u. So this is now our general formula for integration by parts. So as you can see, we have an integral on the left side, and we have two functions on the right side. The first one would just be the product of u and v, so there is no integration involved here. You just need to multiply u and v, but of course you need to first identify what is u and what is v, so there is some integration involved in that. But for when you write down your answer, you just, the first part of the answer will just be the product of those two, and then the second part is negative integral or minus the integral of v du. So now you have an idea that what we, from the integral u dv, we need to somehow transform the equation or the problem into the integral of v times du. So now let's try to establish some rules on what is u and what should be dv. So again, rewritten here is the general formula for integration by parts. So I hope you just get used to the mnemonics of it. u dv equals uv minus v du. Just remember where you put the integral signs. So the integral u dv is equal to uv minus v du. So keep this formula in mind. Okay, so here we have some notes on choosing what is u and what is dv. Okay, so the first one is to choose u so that du over dx, or the derivative of u, is simpler. Okay, so I know there is really no mathematical explanation in this, but on the next examples you will see what we mean. So that is really not just this is like it's not like steps. Okay, so this two should be, you should filter what is u and what is dv using these two simple rules. The second one is to choose u so that the integral of v is possible. So I think every integral is actually possible, but it depends on the difficulty. So if you can see that the integral of v will give you difficulty, I think you should consider interchanging your choices for u and for v. So this would be, you will understand this what do you call this, rule of thumbs easier with examples. So let's take an example. Let's have the integral x ln x dx. So first of all, before you proceed doing integration by parts, you should try to check first if you can do simpler integration techniques in this, like if you can do u substitution, or if you can find it in your integration tables, or it fits an integration formula, so you can just use that before you jump into u substitution. So for our first example, let's have this one, x ln x dx. So the trick here is to try to find what is u and what is v first. So as you can see, we have x and ln x as our choices for u and what is dv. So first, let's use u and apply our filters. So let's say you choose x as your u. So the first filter is choose u so that du is simpler. So in this case, what would be du? That would be dx or 1, right? So that looks simpler, right? Now let's see what happens to what would be v. So recall that v would be, if you choose x as your u, v would be what's left, what is everything, okay, minus u. So that would be the integral ln x dx. Okay, so for our second filter, so choose u so that v would be possible. So what is the integral of ln x dx? So does it look simple and does it look possible? So I think at this point we don't have a technique, or it's not even in the integration table for this function, the integral ln x dx. So if you encounter such a roadblock, I think it's a good idea to try to reverse your choice for u and u and v. Okay, so now let's go with u as ln x. I hope you are getting the idea of how we analyze and what are our filters in choosing u and v. So if we have u equals ln x, the derivative of that would be, so we know that the integral of dx over x is equal to ln x. So if we take the derivative of ln x, that would just be equal to 1 over x dx. Okay, so for v, we write v as what is left. Okay, so we took ln x, so then v would just be equal to x dx, or the integral of x dx, or that would be equal to simple power formula, that would be x squared over 2. So for our, when we first choose u as x, the derivative of u is just equal to dx, so, or 1 dx. That is actually simpler than this 1 over x dx. But for that first choice, v is difficult to integrate compared to this one, right? So v is equal to the integral of x dx, simple power formula, and that will just give us x squared over 2. We actually can write here plus c, but you will realize later that writing plus c will not be needed, as it will just be cancelled in the final answer, the c for this one. But the c for this problem here wouldn't be cancelled. You need to write it down since we are evaluating indefinite integrals. Okay, so I hope you understand a bit how you filter which would be u and what would be v. Okay, so now, okay, we still have one left. We need the dv would just be x dx. The integral of that would be v, which is x squared over 2. So now we have a value for u, we have a value for du, we have a value for v, and we have a value for dv. It's time to plug in these values to our general formula, which is the formula for integration by parts. So now that we have written down our equation, or identified our equation as u dv, let me write it down here. We have here, this is our u and this is our dv. So our equation now takes the form u dv. So we can write our answer as uv minus integral of v du. So our I just want to emphasize here the integral v du, because this is our problem now, right? From u dv, our problem is to integrate v du. That's why we established our rules. We need the integral v to be possible and du to be simple, so that we can integrate v times du. Okay, so now let's plug in our values here in our solution. So our first answer for the integral of x ln x dx, that's integral of u dv, that would just be equal to u times v. So u is ln x. Alright, let me write that down in different color. So u is ln x, v is x squared over 2. So that is the first part of our answer. You just multiply u times v once you identify them correctly. So the next part would be the integral of v. This is v, so we need to write v twice on the answer, right? So you have x squared over 2, and you multiply that with the derivative of u, which is in this case 1 over x dx. Let me just write here dx. Okay, so to simplify our answer, let's do the practice of writing down the polynomial first before the ln. So x squared ln x, that is the first part, and we are left with the problem how to integrate x squared over 2 times dx over x. So as you can see, we can cancel 1x from here. So what we are essentially left with is x dx over 2. So I hope you can follow the algebra in that. So this is x squared divided by x. That would just be x times dx divided by 2. So this is, we are left with this integral here that is easier to integrate compared to x ln x dx, right? So first, our problem is to integrate u dv, and we transform it in such a way that we need to integrate v du. In this case, v du is easier to integrate, as you can see here, right? This is easier. So I hope you haven't forgotten your fundamentals from our earlier topics. So let me write it down here. We have x squared over 2 ln x. Still, this is u times v minus, we just take out the constant 1/2 and we integrate x dx. So our answer should look like this: x squared over 2 ln x minus 1/2. This would be x squared over 2, or minus 1/2 times 1/2. That would be 1/4 x squared. And for the final answer, you should write your plus c. So can we simplify the this answer? Yes, we can simplify it further by factoring we can factor out what? We can factor out 1/2, right? So let me take this and this. So make it a practice to always simplify your answer. Sorry, we actually can factor out x squared as well. So let me write this down in such a way. So this is our final answer here. We factor out x squared over 2. So this is our final answer. Let's take another example. So let's have the integral of ln x squared dx. So first you will check if an integration formula will fit this problem. So in that case, you don't have to do integration by parts. But if you see that it doesn't fit any integration formula, or you cannot do even u substitution on it, then useful technique would be to integrate by parts. So for this one, first step, again, identify what is u and what is v. So for this, I think we really have no choice but to make ln x squared as our u, and whatever remains would be our v. So v would be the integral of dx or x. So to take the derivative of u, so using this is just chain rule, so ln x squared, so that would be 2, reduce the power, 2 ln x, and take the derivative. The derivative of ln x would be dx over x. So I hope you can follow that one. That is chain rule for differentiation. And for dv, of course, that would be equal to dx. Okay, so again, writing down our general formula for integration by parts, you have u dv, you already identified u and dv, which is ln x squared dx. That would be equal to uv minus the integral of v du. So this is v is x, du is 2 ln x dx over x. So plugging that in on our equation, so the integral of ln x squared dx would be equal to uv. That would be, so in this case, I would like to put the ln after, so we will go with vu. So that would be x ln x squared, that is for u times v. Then what remains is minus the integral of v du. So v is x times 2 ln x dx over x. So let me write that down as v, let's put it in red. V is x multiplied by 2 ln x dx over x. As you can see, we can cancel out this x, so what remains would be our answer. Let me do this here. Let me write that down again. That would be x ln x squared minus, that would be, you cancel x, so you can put the constant outside the integral sign. So we are left with ln x dx. Alright, so this is a familiar problem. We already encountered this from the first example. So what is the integral of ln x dx? Again, we didn't choose this as our u earlier, since, or rather our v or dv earlier, since we don't have the answer for integral of ln x yet. But here we can see how to take the integral of ln x. And what do you think we should do? So let's take that answer first as it is, and let's solve what is ln x. So let's take the integral of ln x dx. So for this, let's use u bar so that you won't be confused, and v bar. Okay. So for this one, what should be our u? So of course, we take ln x as our u, so that we can take the derivative of u bar as, so we take dx over x is equal, the integral of dx over x is equal to ln x. Therefore, the derivative of ln x is just dx over x. And again, v bar would be what remains. So the integral of dx, or that's equal to x, and dv bar, or the derivative of v bar, would just be, of course, dx. Okay. So writing down again, plugging in our values for our integration by parts formula, that's u dv uv minus v du. Let me do that in this part here. Okay, so the integral of ln x dx would just be equal to u times v. That would be, or sorry, let me, so that you won't be confused, let's write u bar here as well. So that's u bar, uv bar, and everything. Okay, so we are doing this because, as you notice, we carried out another integration by parts within integration by parts. So we did it twice. So that you won't be confused, let's just name everything with u bar at the top. Okay, so u bar is equal to ln x. So let me write first what is the v first. So that would be x ln x that's the first part, minus the integral. What is our integral? Here we have v bar, that's x, and derivative of u, that's dx over x. So v bar would be x, and the derivative of u bar is dx over x, where we can just cancel the x and get the integral of. So this would be, I will write it down again as x ln x minus the integral of dx, or the integral of ln x dx would be equal to x ln x minus x. of course, that would be plus c, since you're still evaluating an indefinite integral, so don't forget about your constant. So I know we already jumped into definite integral in area where we eliminated this c, but now we're dealing again with definite integral, so we need this constant of integration again. Okay, so this is not yet the final answer, since we have to go back to our original answer, which is here. We need the answer for the integral of ln x dx. I think I should do that with another. Okay, let's do that with another page. Okay, so let me write down, that's x ln x squared minus 2. The original equation is ln x squared dx, and so far our answer is x ln x squared minus 2 ln x dx. That's x ln x squared minus 2. The integral of ln x dx we found to be x ln x minus x plus c. Let us call this as c1. Okay, x ln x minus x plus c1. So that's 2 times x ln x minus x plus c1. So again, we evaluated an indefinite integral, so we need to have another constant of integration. Let's call it c2. Okay, so now let's simplify our answer. So what do we have? We have x ln x squared minus, let's just distribute, that's 2 x ln x minus, or that would be plus 2x plus 2c1 plus c2. Alright, so this is 2c1, this is still a constant, and this is c2, another constant. So we can combine both of this into one arbitrary constant, which we will call as c. But at this point, again, it's good practice to simplify your answer always, to factor out what needs to be, so that you won't be need to write everything. So the integral of ln x squared dx would just be equal to, so what can we factor out here? So first we can factor out, for the first one, we can have x ln x, is that correct? Right, multiplied by x ln x, this would be ln x only, minus 2, and we have plus 2x, and these two arbitrary constants can be called as a single arbitrary constant, c. Okay, so that is our final answer for the integral of ln x squared dx. So as you notice, you will encounter a time where you need to do integration by parts twice. So that's integration by parts within integration by parts. So the key here is just not to be confused by writing everything down. Okay? So the first step, identify what is your U, what is your DU, what is V and DV. And first of all, again, what you need to have is the skill to do derivatives and antiderivatives. Just like this one, if you pick your ln x squared as your U, you need to know how to take the derivative of that, and that is by using the chain rule for differentiation. That's 2 ln x times, that's basically the power formula with the du here, which is dx over x. Okay, so first of all, you need to know how to differentiate. That is the prerequisite to this subject after all, and you need to do it in a quick manner. Alright, so you can't spend all your time with just a single problem, because as you can see in your tests, you have multiple problems and you need to manage your time. So for that, you need to identify properly what is U. So because earlier if we do trial and error in picking U and what is DV, you will encounter a roadblock, and that's not a problem if you're just beginning to learn the technique. You just have to learn from your mistakes and reverse your choice for U and DV. But in the test, you should have developed the skill enough to do integration by parts, and you do that by practicing. That's why we are giving out a lot of problem sets for you to practice, which I hope you are doing by yourself, so that when it comes to the assessments, you will do it in a quicker pace. Okay, so the first thing is you need to know how to do derivatives and antiderivatives without getting confused, right? Because the earlier, if I ask you what is the integral of ln x dx, you might tell me it's dx over x, but you know that that's the other way around. The integral of dx over x is ln x, so it's somehow confusing, right? So you need to know how to do derivatives and antiderivatives, and again, the key is to write everything down. So here we encountered the roadblock, that is the integral of ln x dx, where we need to do integration by parts again. So in order for us to not be confused, we just rename our variables. We just put a bar here, so that's u bar and v bar. And again, the same process, identify what is your u, what is your v. Remember the original rules of thumb, which is to choose u so that the du would be simpler, and choose u so that the integral of v is possible. So we did that because we need to transform the problem into something where we will integrate v du. So we need to be able to integrate v and for du to be as simple as possible, because we are going to multiply them. Okay, so I hope this is just the second example, but I hope you are getting the idea and you are getting some techniques out of it. And I just want to share here, we have, through the years, they developed this is an acronym for you to follow in choosing u. So if I can recall correctly, L is for logarithms, I is for inverse of everything, that's inverse sine, inverse tangent. P is for polynomial. That's your x. Sometimes they replace it with a. They call it algebraic. So that I prefer to do it this way so that you can have an acronym that you can memorize. So in this case, it's LIPIT. E is for exponential. Okay, exponential, that would be e to the x. And T is for trigonometric. So as you practice your integration by parts, you will realize later that E and T are interchangeable. Sometimes it's called, the acronym is LIPTE or LIPET. Okay, so this succession is your criteria for choosing you. For me, I prefer the first two rule of thumbs that we did, but that's really not exact, right? So this one, they developed it. I don't know who invented this, but if you search in anywhere in modern books or videos, they will give you this acronym, the hierarchy for choosing you. So how does it work? If you see a logarithm or an ln, anything logarithm or natural logarithm, you choose that as your you prioritize that as your okay. So the next one would be an inverse. Sorry, this is inverse. And if you see inverse trigo, you use that as your u. Okay, so I hope you can follow the idea of the acronym they invented for you to choose what is the u, and what remains would be the v, the integral of whatever remains. Okay, so for our third example, let's have the integral of e to the x sine x dx. So now that we know that we can just write ex as its derivative and its antiderivative, right? But now that we have learned the technique for identifying what should be chosen as u, which is LIPET or LIPET. So this is exponential and this is trigonometric. So exponential comes first, right? Than trigonometric. Therefore, we choose e to the x as our u. And therefore, the derivative of that would be the same thing, except we have a dx. And our v would be what remains. So v is equal to, we took e x, so v is equal to the integral of sine x dx, or that is negative cosine x. And the derivative of that would be sine x dx. Now again, writing down our general formula, u dv uv minus integral v du. So we already identified everything, right? U du v dv. So our problem is now of the form u which is ex times dv, which is sine x dx. So we can proceed now with our integration. So let me just write it here, the equal sign. So the first part would be uv, which is ex, v being negative cosine x. So that is the first part. And the second part would be the integral of v du. V is, let me correct this. Oh yeah, that's correct. I'm sorry. That's uv. And v, we will just write it here again. That would be negative cosine x multiplied by ex dx. Okay, so we know how to integrate this. It's basically the same thing as before, right? There's an ex dx, and we just replace the sine x, which is a trigonometric function, with negative cosine x dx. So you guessed it right, we need to do integration by parts again. So just for this one. Okay, so let us write that down in a separate problem. So that is basically negative cosine of x e to the x dx. Again, we need to identify what is u. In this case, this is still exponential versus trigonometric. So our u would be e to the x, and the derivative of that is still e to the x dx. And the v would be whatever remains. That would be the integral of negative cosine x dx, which we know is, we take negative 1 outside, that is still negative sine x, and the derivative of v would be equal to negative cosine x dx. So writing down again, that would be, so I'm sorry if I'm writing this equation every time. I just want you to have a knack of it or memorize it. I hope you get used to the mnemonics of it. UDV, UV, VDU. Okay, again, writing down this integral would just be equal to UV, that would be E. Okay, let's stick to the numbers or our color code. That would be UV EX multiplied by V negative sine X minus the integral. What's this? We have V du, which is negative sine X EX dx. So that's negative sine X. I'm sorry, I stopped sticking with our color code. Let me write that down again as, that's V negative sine X du, which is ex dx. Alright, so look at this. This is basically our original problem, right? Ex sine x dx, but this time it's negative, right? Okay, so writing down, plugging it for the integral of negative cosine x ex dx. Again, don't forget you have plus c. Okay, so let's write that down as, I think we should just go back to the original one. Okay, so we substitute this one, we sub this one. Let me divide that here. So our answer as of now is the integral of ex sine x dx is equal to e to the x times negative cosine x minus, we already evaluated this as ex times negative sine x minus this integral here. Or in order to evaluate this integral, we can take the negative sign out, so that would be plus. Okay, so we go back here and that's minus, so don't forget the brackets. So minus this ex to the negative, times negative sine x minus the integral, or in this case this would be plus, right? We just want to write down the second answer as similar to the first one. Okay, so does that make sense to you? I hope it does. So do we need to do integration by parts again? No, we just simply need to recognize the fact that we have similar functions from the left and to the right. Okay, so let me just make this clear. This would be e to the x times negative cosine x minus this would be e to the x times negative sine x plus the integral of the same thing, our original problem here, ex sine x dx. So if we apply this negative sign here, we can write it down. Let me just write it down in new form. Okay, so our problem is e to the x sine x dx. So the key here is just to write everything as it is and not miss anything. Okay, so here it's, let me write it down where the negative sign would be outside. So that's negative cosine x. Okay, let's just write this as it is so that you won't be confused. So that's e to the x negative cosine x or that would be plus, since we took the negative sign here, that would be plus e to the x times sine x. So that's positive now since we took the negative sign. And that would be minus the integral of our original problem, which is ex sine x dx. So what we need to do here is just transpose this one to the left side. So now we are left with 2. So this will become positive. So that's the integral of e to the x sine x dx. So twice that. So 2 times e to the x sine x dx would be equal to, I would like to factor this out at this point. So we can factor out e to the x. That would be sine x minus cosine x. So I hope you are not having a problem with the algebra that we are doing. So now the last thing we need to do is just write it down. So this is 2 times our integral. So if we divide the other side with that, so that is the answer for our integral. So that's ex sine x dx equals e to the x over 2 times sine x minus cosine x. So again, remember we have here a plus c, right? Somewhere here we have a plus c, but that would be plus c divided by 2. So that's another, still a constant. So let's just call it as c. Okay, so our answer would be e to the x divided by 2 times sine x minus cosine x plus c. That is our integral for e to the x sine x dx. So you notice here, when you encountered the same problem, e to the x sine x dx, you thought you would be stuck in a loop, right? But essentially that is just our original problem. So we'll just do the algebra and find our answer in such a way. Okay, so let me just recap that. So we integrate by parts our original problem, which is ex sine x dx. We found this first answer here by u substitution, e to the x minus cosine x minus another integral needing integration by parts, which looks similar to our original problem. It's still an exponential function and a trigonometric function. So we do integration by parts a second time and we arrive at this answer. Let's just check. That's ex times negative sine x minus the integral negative sine x ex dx. So I hope you can follow the algebra, you can follow how the derivatives, how to get the derivative for some sine and cosine. I hope at this point that you're not getting confused with that. For the tangent, secant, and others, I won't take it against you if you haven't memorized it, but I hope you already know how to do the derivative and antiderivative of sine x and cosine x and back. If you are confused, just check your tables, but it will be very useful if you already have that in mind. Just for sine and cosine, the others you can look it up in the tables. Okay, so now it occurs again, our original problem. That's why, so we write down everything and we simplify everything, and now we transpose this same integral the other side. So we got twice that, and since we got twice that, we just need to divide the right side with 2 to get our answer. Okay, so I hope you did follow that. So now let's do a fourth example. This one is very interesting just because you will do another form of substitution here. So let's have x cubed e to the x squared dx. So as you know this, we have an exponential function, but the exponent is it's nonlinear. It's x squared. So the first thing to do is to try to linearize the exponent, and we do that by substituting another variable. Let's call w. So we let w equals our x squared. Okay, so later on this would become e to the w. We just want to operate with a linear exponent. Okay, so we take the derivative of that would be dw, that would be 2x dx. So that's 2x dx. So plugging in here, we want to transform this equation such into terms of w. Alright, so this, if we want to plug 2x dx in there, we need to take an x here, right? So that means we need to plug, this would become x squared since we're going to take 2x dx. This would become e to the w. So that's e to the x squared, or w, times dw, which is 2x dx, or let's just write that down as, I will write it down here so that you won't be confused. Since we introduced 2 here, we need to divide it by 1/2 outside, right? So that is just equal to 1. So what I want you to see here is this equation would just be equal to the equation that we are rewriting here. Or in terms of w, that would be equal to 1/2 integral x squared e to the, x squared is w. Okay, w is equal to x squared, so we write it as w e to the w, 2x dx is dw. Okay, so now we are left with this problem. So we can use integration by parts on this problem here, and we just proved that this equation is just the same as this equation, and we will just substitute everything back after to our original equation in terms of x. So now, identifying u, we have learned earlier that polynomial or algebraic expression will go first before exponential. That's PET, right? LIPET. So polynomial comes before exponential. Therefore, our selection of u must be w. And the derivative of u is dw. And for v, the integral of e w dw, or e to the w. So dv would be e to the w dw. And now what we need to do is to plug in our equation for integration by parts, which is the integral u dv uv minus the integral v du. I hope at this time you already memorized this. Now let's go plug in our values. So remember, we are operating on terms of w here. So this integral would be equal to, remember that we have a 1/2 outside. Okay, so that's uv. U is w, v, that's, let's color code that again, stick to our color code. That's uv, that's w, v is ew, e to the w minus the integral of v du, which is, in this case, v is again ew, du is tw. So that is an easier integral, right? ew dw would just be equal to e w. Okay, so our answer is 1/2 of that. Okay, so let me write that down in black this time. Okay, so that would be equals w e to the w minus the integral of this is just e to the w, and we need to take 1/2 of that. So our answer would be all of that over 2. Of course, don't forget the plus c. Now, substituting everything back, since our original problem is in terms of x, we need to substitute everything. So this would be w, that would be, this is our final answer here. Let me write it down as, okay, let me use a new one. So the integral for x cubed e to the x squared dx would be equal to this one here, w e to the w minus e to the w. Actually, we can simplify this by taking e to the w times w minus 1 all over 2 plus c. So now we need to substitute our values for this. Okay, so basically our answer would be e to the w, which is x squared, right? E to the x squared multiplied by w, which is x squared, minus 1 all over 2 plus c. So this is our answer. So this is just a method of operating on an exponential function with a non-linear exponent. You can linearize it by substituting it with a w, and then transform your equation. Don't change anything in your equation. Make sure that it is still equal to the original equation, and you already have a lot of practice with that, right? Introducing 2 here, dividing it by 1/2, that's just the same as multiplying it by 1. And here you got the transformation of your equation. So this one is an interesting technique that you can put in your toolbox or in your skill box in case you need to encounter some problems with exponential functions with a nonlinear exponent. So our source for this is still our reference book, The Calculus 7 by Louis Lithold. Yes, it can be found in pages 574 to 583. That's other integration techniques. You can study the other examples there for your reference and for your practice as well. So if you have any questions or clarifications, just use our Q&A form that is uploaded together with this material, or you can just you can also send an email, but it's better for you to use the Q&A form so that your classmates can also see your questions and they can also see the replies to that or the answers. Okay, so as always, thank you for your attention, and I hope you learned something today. Thank you and good luck.